Today we will be deriving the energy-momentum relation, which is of enormous importance for wave-particle duality, and indeed many of the fundamental equations in quantum physics. We will see that you can derive the Schrödinger equation from the energy-momentum relation. So we're going to start this one with a postulate. I normally don't do this. I might circle back at a later date and explain this further, but we are going to start with a postulate that epsilon, which I've used that symbol before, the total energy of a system epsilon, we're going to say as a postulate it's equal to gamma times the rest mass, which we're going to be talking about in this video, times c squared. Okay, and we've seen gamma before. We've seen gamma as a function of v, and I think in my last video I wrote it as c over the square root of c squared minus v squared. We're going to rewrite it slightly. Divide top and bottom by c. That c on the bottom comes in under the square root as a c squared. So we get 1 over the square root of 1 minus v squared over c squared. And this is the more standard way you will see gamma as a function of speed. Okay, so the first thing we want to really start with is our goal is going to be to rewrite gamma as a function of p, as a function of momentum. What is that? Well, we need to talk about what is relativistic momentum. So that is obviously a part of the energy momentum relation. So imagine that we have an origin reference frame, or a stationary reference frame, which I'll call O. And then we imagine we have an object that's moving with mass m naught, rest mass. And rest mass is simply the mass of the object when its speed is 0. It's moving at speed v. It's not accelerating. And then what we have over here, what in some literature is called the lab frame. And the lab frame is not the stationary reference frame. It should be important to note that. The way I think about the lab frame is that when the object is in the frame, you are actually in the primed reference frame because you are sort of alongside the object as it bounces back and forth. And if we recall, the photon that travels within the lab frame, okay, so the photon that travels, the photon that travels the length of the object in the lab frame is going to be equal to x prime equals gamma times the length outside the lab frame, which is L. Okay, or from the origin's standpoint, the origin reference frame thinks the length of the object is L. Okay, so to get the relativistic momentum, what we're going to do is we're going to show that P is equal to gamma times the rest mass times V. It's not difficult to show. And all we're saying really is that gamma m naught is equal to some mass m. Okay? And of course P equals mv is our standard equation for momentum. So if you imagine that you have a length of your object up here, and we're going to say that some mass mx is going to be equal to sigma, which is, say, the mass per unit length times that length. Well, we're going to say that the length capital L in the lab frame, the length capital L here, well, capital L is simply just x prime. It's the amount of time it takes a photon to travel in the lab frame. Okay, and well, x prime is simply gamma times lowercase l. Okay, so mx in the lab frame, or mx prime in the lab frame, is clearly going to be L times sigma, right? Sigma is the mass per unit length, and the length has contracted. So capital L is just gamma L times sigma, and we know that sigma L is equal to mx. So this is clearly equal to gamma times mx. So this is what we mean by this is the m, and this is the rest mass. Rest mass. Okay, so I think I hope this derivation has been clear enough, but this is why we can say that P equals gamma times m naught v, where, like I said, this mx really is m naught in that definition. Okay, so that gives us a little bit more to move forward with. So let's give ourselves some space, move down here. We know that P equals gamma m naught v, and then gamma as a function of v is equal to 1 over the square root of 1 minus v squared over c squared. Okay, so we're going to first square P, and you get gamma squared m naught squared v squared, and that gives you m naught squared v squared all over 1 minus v squared over c squared. We're going to bring, we're going to bring the denominator up top there, and we're going to get p squared minus p squared times v squared over c squared equals m naught squared v squared. All right, let's bring all of the v squareds together. So we get p squared equals v squared outside of m naught squared plus p squared over c squared. And then, of course, v squared is going to be equal to p squared over m naught squared plus p squared over c squared. Now we're going to multiply by c squared, and this is motivated by the next step that I want to do. So this gives us p squared c squared all over m naught squared c squared plus p squared. Okay, well, why did I do that? Well, we're trying to get this quantity, v squared over c squared. So if I calculate v squared over c squared, clearly that's going to be equal to this, and just divide out the c squared on top, which is p squared over m naught squared c squared plus p squared. Okay, so gamma now as a function of p is going to be equal to 1 over all under the root here. And we know the first term is 1. And what I'm going to do is I'm going to normalize this to the denominator here, so this denominator. So we're going to do m naught squared c squared plus p squared all over m naught squared c squared plus p squared, and then minus p squared, right? Because it's this guy. We're doing subtract there. Okay, so then the last step, obviously, well, our p's cancel. That's nice. And then this whole thing flips and becomes m naught squared. Sorry, let me write this root bigger. M naught squared c squared plus p squared all over m naught squared c squared. And this, of course, reduces to 1 plus p over m naught c all squared. Okay, so that's what I wanted to show in the first video. And this is the, let's use a different color. This is the standard way that gamma, which is that length contraction factor, is written as a function of momentum. So this is kind of considered like the for massive particles. It's sometimes written. This is the relationship for massive particles. All right, so I'm going to stop this one here. We will pick up the next video from here and continue our discussions on the energy momentum relation. Thanks for watching. Please like and subscribe, and I'll see you next time.